Now that we've seen how to solve ConCoHomLinDEs and non-homogeneous linear equations with constant coefficients, as long as the right-hand side is of a certain form, let's apply that to sort of a seasonal topic, modeling the motion of a spring. So whenever you do a mathematical model of something, you need to state your assumptions and try to turn those assumptions into equations, mathematical objects that you can deal with. So we're going to make the following assumptions, and in general, in real life, these aren't ever satisfied, but as a first approximation, we're going to make these assumptions. So the first one is that the spring obeys Hooke's law. We've talked about that before. That's F equals minus ky, so the force of the spring is proportional to how far you stretch the spring. We're going to assume that the spring has no mass of its own, meaning the actual coils of the spring don't weigh anything. We're going to attach a constant mass to the end of the spring. We'll call that mass m. And we're going to assume that there is a damping force. That is to say, a force which acts to slow the motion of the end of the spring down, proportional to the velocity at the end of the spring. We can represent that with the equation Fd, the damping force, is minus some constant times dy dt. And this is how fluid resistance works. Air resistance, resistance in water, any fluid like that, the faster you go, the more it pushes back on you. These first two assumptions are known as an ideal spring. So a spring that has no mass of its own but obeys Hooke's law is called an ideal spring. Okay, so these are our assumptions, and you can see that we've encoded two of them as equations and one of them as a number, the mass, m. Let's go ahead and make an equation that represents the whole system. Newton tells us that all of the forces acting on the system have to balance with each other. So on the left, you have the force due to acceleration, and on the right, you've got the damping force and the force due to the spring, and those have to balance out because this is a physical system. So let's carry everything over to the left-hand side and kind of clean it up a little bit. Remember, we always want to make sure that our leading coefficient is 1. And there we go. We have a ConCoHomLinDE that is going to model this system. So the motion y of t of the end of the spring has to satisfy this equation. So if we solve this equation, we know how springs work. So how do we solve a ConCoHomLinDE? We need to write down the linear operator as a polynomial in D. Now we need to find the roots of that thing. It's quadratic, so the nice thing is we know how to find the roots of a quadratic. Let's clean that up algebraically just a tad. So we have two roots, and then you can see the important question is, what's the sign of this c squared minus 4km? Well, there's a few different cases. The first case is, what if c squared is less than 4km? Of course, when you get two complex roots, they occur in conjugate pairs. That's what the plus minus is about. And given these particular roots, we actually know how to solve the ConCoHomLinDE. To make the solution easier to state, I'm going to call this number mu. So my solution is going to be something times e to the minus c over 2mt times cosine mu t plus something times e to the minus c over 2mt times sine mu t. Great, we've got it. Let's figure out what that looks like. I just wanted to go ahead and graph them. To make things a little bit easier, I'm assuming the mass is 1/2. And then if you just work out the formulas, plug them in. I've got little sliders here for C1 and C2, so I can change those. Those correspond to changing the initial position and the initial velocity. And then I can also change the constants of the system, right? So remember, C is this damping constant. It's sort of how viscous the fluid you're moving through is. And K is the spring constant. It's how springy the spring is. So you can see right now, we've got c squared minus 4km is negative, which is the situation we're interested in. And let's just take a look at it, right? What does it look like? It looks like this sort of sinusoidal wave that's dying off. Right? So we can kind of play around with that to see what happens as we change the constants. You can see as you increase the damping constant, right, you make it move through a thicker and thicker fluid, well, it's going to be a little bit less oscillatory, right? Whereas if you put that thing really low, you get a bunch of oscillations. They're still dying off. How are they dying off? They're dying off exponentially. This is sometimes called the envelope, these two exponential functions here, and inside that you're oscillating. Now this situation where c squared is less than 4km is known as underdamping. And you can see it looks like an exponentially decaying sinusoidal wave. The period of that wave is just given by looking at the period of these two, which is 2 pi over mu, and that's called the quasi-period of the oscillating system. Of course, it's not actually oscillating, right, because it's being hit with this e to the minus c over 2mt, so it's decaying, but it still sort of looks periodic, and the sort of period, or the quasi-period, is 2 pi over mu. Now, if it so happens that c squared equals 4km, that means that this square root part of the quadratic formula is 0, then we're going to get a repeated root. It's going to be minus c over 2m, and it's going to occur twice. We know how to solve that. Let's take a look and see what that looks like. You can see that it's a little bit different, right? We're going to have, in this case, one swing, right? So there's the base position, and we've swung through the base position, and then we're going to come back and decay towards it. If we change the parameters c1 and c2, which corresponds to changing the initial position and the initial velocity of the end of the spring, you can see that we might get other behavior, like not even swinging through the base once, right? So swinging through the base means hitting 0 here. And as you vary, you can see sometimes it doesn't even swing once, sometimes it swings once. But in any case, the most number of oscillations this thing passes through is sort of like half an oscillation. This is known as critical damping because it's the amount of damping that means there's no further oscillation in the system. So with underdamping, the system still oscillates. With critical damping, you get at most one bounce, and then we decay off. The remaining case is what happens if c squared is greater than 4km. Okay, and those roots are going to be minus c over 2m plus or minus the square root of c squared minus 4km over 2m. And again, I'm going to label this plus or minus part, I'm going to label that mu. Notice it's a different mu from above. And that's just to make things a little bit easier to write down. So our solution is going to be a linear combination of two terms, each of which has exponential decay. Notice we can actually factor out the t's from that. So you can see that this is exponential decay. Now, if we really wanted to, we could rewrite this in terms of hyperbolic sine and hyperbolic cosine, where we still have a mu t inside cosh and sinh. Of course, the coefficients are going to be different, right? If the coefficients c1 and c2 were both 1/2, that's going to give you cosh. If they're 1/2 and minus 1/2, that'll give you sinh, and anything in between. Cosh mu t and sinh mu t have the same span as e to the mu t and e to the minus mu t. The only reason to do that is that it makes the whole picture look a little more symmetric if you want to compare to the situation of underdamping. So this situation where c squared is greater than 4m is known as overdamping, and you can see there's no oscillations at all. You can see it's really just exponential decay, right? There's nothing super interesting going on here.